Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University, National Cheng Kung University. Welcome to the course Introduction to Seismic Design of Structures, Lecture 13-1, Small to Moderate Seismic Force. In previous lectures, we talked about design basis seismic force and maximum considered seismic force. And in this lecture, we will focus on small to moderate seismic force. Small to moderate seismic force is the seismic force corresponding to small to moderate earthquake. And here's terminology. Small to moderate earthquake, in Chinese, 中小度地震, is an earthquake level with 80% of exceedance in 50 years. In Chinese, 50年内 80% 超越几率的地震等级. Or is an earthquake level with 31-year return period. In Chinese, 31年回归期之地震等级. And a small to moderate earthquake is an earthquake level with 80% probability of exceedance in 50 years from the Seismic Design Code Section 2-2.10.1. Let X be the number of earthquakes exceeding the small to moderate earthquakes in 50 years. And the distribution of X is Poisson distribution, and X is a random number. Since the probability of exceedance is 80% in 50 years, there may be one earthquake exceeding the small to moderate earthquake, maybe two earthquakes, and so on and so forth. Therefore, the probability of x equal to 1 plus the probability of x equal to 2 plus and so on and so forth equal to 80%, corresponding to 80% of exceedance in 50 years. Therefore, it can be written as summation from x equal to 1 to infinity, probability of x equal to k, summation from k equal to 1 to infinity, probability x equal to k equal to 0.8. From the probability that the summation of probability equal to 1, therefore the summation here can be expressed as 1 minus probability of x equal to 0 equal to 0.8, and after rearrangement we have probability of x equal to 0 equal to 0.2, 20%. Therefore, 80% probability of exceedance in 50 years is equivalent to that the probability that no earthquake exceeding the small to moderate earthquake in 50 years is 20%. Probability of x equal to 0 equal to 0.2, and from the Poisson distribution, when probability of x equal to 0 equal to lambda t to the power 0 equal to 1 times exponential minus lambda t divided by 0 factorial, and 0 factorial equal to 1. Therefore, we have exponential minus lambda t equal to 0.2, and take natural logarithm to the both sides of the equation, then we have minus lambda t equal to log, natural log 0.20, and then we have lambda t equal to minus natural log 0.20, and t equal to 50 years. So that from this equation, we can solve for lambda equal to 1 over 31 years. Therefore, in 1 year, the average number of earthquakes exceeding the small to moderate earthquake is 1 over 31 times in 1 year. Therefore, on average, there will be one earthquake exceeding the small to moderate earthquake in 31 years. Therefore, the return period of small to moderate earthquake is 31 years. Therefore, the small to moderate earthquake is an earthquake level with 80% probability of exceedance in 50 years, or is an earthquake level with return period of 31 years. Now we have lambda equal to 1 over 31 years, t equal to 50, and x is the number of earthquakes exceeding the small to moderate earthquake in 50 years. Probability of x equal to 0 equal to lambda t to the power 0 equal to 1 times exponential minus lambda t, lambda equal to 1 over 31, and t equal to 50. 0 factorial equal to 1. After the computation, we have the probability of x equal to 0 equal to 0.1993, and probability of x equal to 1 equal to lambda t to the power 1 times exponential minus lambda t divided by 1 factorial equal to 0.3215, and probability of x equal to 2 equal to lambda t square times exponential minus lambda t divided by 2 factorial equal to 0.2592, and probability of x equal to 3 equal to lambda t cubic times exponential minus lambda t divided by 3 factorial equal to 0.1394. From here, the probability that no earthquake exceeding the small to moderate earthquake in 50 years is about 0.2, that's 20%. If there will be one or more earthquake exceeding the small to moderate earthquake in 50 years, is the summation of all this probability is approximately equal to 0.80. That's 80% probability of exceedance in 50 years. Let us go back to consider the design-based seismic force, and V equal to I divided by 1.4 alpha y times SAD divided by FU modification and W. And FU here is the seismic force reduction factor for the structural system due to ductility. Okay, when the structural vibration period becomes longer and longer, the FU, the reduction factors, becomes larger and larger. Then the design seismic force becomes smaller and smaller. The structure resists a design-based earthquake by developing allowable ductility capacity, RA, so that the structure will enter into inelastic range. Therefore, the structure may be moderately or severe damage. Since the design-based seismic force is reduced, so under small to moderate earthquake, the structure may yield even under small to moderate earthquake. Therefore, minor damage may be resulted. Since the small to moderate earthquake occurs frequently, so that there may be some minor damage frequently. In order to avoid this situation, we introduce, in addition to design-based earthquake, maximum considered earthquake, we introduce small to moderate earthquake. There will be 80% probability of exceedance in 50 years, and the return period of this earthquake level is 31 years. Under small to moderate earthquake, the structure is designed to remain elastic, so that no ductility will be developed, so that the structure, no structural damage occurs in the structure. This is taken from the Seismic Design Code, section 2.10.1. Then we move to small to moderate spectral acceleration. Spectral acceleration with return period of 31 years is about 1/4 that of the return period with 475 years. Therefore, the small to moderate spectral acceleration is about 1/4 of the design basis spectral acceleration. This is taken from the Seismic Design Code, section 2.10.1. For the small to moderate seismic force for site class 1, 2, or 3, taken from the Seismic Design Code equation 2-16a, V star is the small to moderate seismic force equal to I times FUD star divided by 4.2 alpha Y times SAD star divided by FU star modification times W. Since the earthquake is small to moderate earthquake, therefore this kind of earthquake will not be induced by the near-fault earthquake. Therefore, it is not induced by the rupture or severe rupture of those faults, active faults. Therefore, no near-fault effect is considered. In the other way, we can say that near-fault adjustment factors NA and NV equal to 1. And there's a question for all of you. Is the small to moderate seismic force always less than the design basis seismic force? Is V star always less than V? That's my question for all of you. And V star equal to I times FU D star divided by 4.2 alpha Y times SAD star divided by FU star modification times W. From previous lecture, we know that the modification of the ratio between SAD star divided by FUD star is always less than or equal to the ratio without modification. According to this inequality, then we have V star less than or equal to I times FU D star divided by 4.2 alpha Y times SAD star divided by FUD star times W. FUD star in the numerator and the SUD star in the denominator, they are cancel out each other, so that we have I times SAD star divided by 4.2 alpha Y times W. Here we have 1 over 4.2. Then it's about 1/4 of the spectral acceleration of the moderate to small to moderate earthquake is about 1/4 of the design basis spectral acceleration. And this one is close to 1/4. Then we move to the small to moderate seismic force for Taipei Basin. For Taipei Basin, according to the Seismic Design Code equation 2-16b, V star equal to 1 times FUD star divided by 3.5 alpha Y times SAD star divided by FUD star modification times W. Please notice that we have 3.5 here instead of 4.2. For site class 1, 2, or 3, we have 4.2 in the denominator. For site class Taipei Basin, we use a 3.5 instead of 4.2. Therefore, the small to moderate seismic force for Taipei Basin is larger than that for site class 1, 2, or 3. Because of basin effect, the earthquake has a longer duration. Therefore, we have to use higher small to moderate seismic force for Taipei Basin. And V star equal to I times FUD star divided by 3.5 alpha Y times SAD star divided by FUD star modification W. From previous lecture, we noticed that the ratio of SAD star to FUD star modification is always less than the ratio before modification. According to this inequality, then we have V star less than or equal to I times FUD star divided by 3.5 alpha Y times SAD star divided by FUD star times W. These two cancel out each other, so that we have V star less than or equal to I times SAD star divided by 3.5 alpha Y W. And here we have 1 over 3.5 here. Then it's very close to 1/4. As the small to moderate spectral acceleration is about 1/4 of the design basis spectral acceleration. And here's a question for all of you. Is V star always less than V? Yes, for Taipei Basin. Is small to moderate seismic force always less than design basis seismic force? That's my question for all of you. And then we go back to the example. A residential building located at Ruishui Township, Hualien County, and within 2 kilometers from Yuli Fault, and the site is hard site. The question is to find small to moderate seismic force V star. For small to moderate earthquake, the earthquake is not induced by the rupture of near active fault, so that NAD equal to 1.40 is replaced by NAD star equal to 1.0. Therefore, the near fault adjustment factor for small to moderate seismic force equal to 1. Once we have NAD star and we have SSD, the multiplication of these two, then we have SSD star equal to 0.8. And then according to the seismic code table 2-2A, then we can have the site amplification factor FAD star equal to 1.0, because SSD star is large enough, and then the site is located at site class 1. Therefore, SAD star equal to 1.0. Once we have SSD, NAD star, and FAD star, and we multiply all the 3 coefficients together, then we have SD star S equal to 0.8. And here's my question for all of you. Is SD star S always less than SDS? From previous lectures, we have already calculated SDS, and then we compare these two. In this case, SD star S is less than SDS. And my question is that, is it always true? And then we move to another parameter, SD star 1, because for small to moderate earthquake, it will not be induced by near fault rupture. Therefore, NVD star is reduced to 1.0. That means that no amplification, no adjustment factor for near fault effect. And then we have S1D equal to 0.45 and NVD star equal to 1.0. And then we multiply these two together. Then we have S1D star equal to 0.45. And from seismic design codes, table 2-2B, then we can have FVD star equal to 1.0. That's the site amplification factor for the periods with constant spectral velocity. Once we have S1D, NV star, and FVD star, and then we multiply these 3 together, then we have SD star 1 equal to 0.45. And in this case, from previous lecture, we can have SD1, and in this case, we have SD star 1 less than SD1. And my question is that, is it always true? Once we have SD star 1 equal to 0.45, SD star S equal to 0.8, and then we divide SD star 1 by SD star S equal to 0.45 divided by 0.8. Then we have 0.56 seconds. That's T0 D star. That's the corner period between short period and medium to long period. And from previous lecture, we have already have the structural vibration period of the structure, T equal to 0.268 seconds. And 0.268 seconds lies between 0.2 T0 D star and T0 D star. Therefore, we have SAD star equal to SD star S equal to 0.8. And from previous lecture, we have already found SAD, and then compare these two, we found that SAD star is less than SAD. And my question is that, is it always true for all the cases, or is case by case? Okay, so far we have T0 star, T0 D star, and also SAD star. Then we are going to find the reduction factor for the seismic force, FUD star. Then we have T equal to 0.268 seconds, and it lies between 0.2 T0 D star and 0.6 T0 D star. Therefore, by looking up seismic design code equation 215, then we can compute FUD star, the seismic force reduction factor for the structural system due to ductility. FUD star equal to square root 2RA minus 1. And RA, from the previous lecture, we know that RA equal to 3.533. And after substituting RA into this equation, we can have FUD star equal to 2.463. And from previous lecture, we know that FU equal to 2.463. And compare this one, then we have FUD star equal to FU. For this case, FUD star equal to FU. That's the seismic force reduction factor for the small to moderate earthquake, equal to that for the design basis earthquake. And my question is that, in this case, equality is held, but for other cases, it's always true. So far, we have SAD star equal to 0.8, FUD star equal to 2.463. And then we can find the ratio between SAD star and FUD star equal to 0.8 divided by 2.463 equal to 0.3248. And from the seismic design code equation 2-2, the ratio here is larger than 0.3. Therefore, modification is necessary. And the modification of the ratio equal to 0.52 times SAD star divided by SUD star plus 0.144 equal to 0.3126. And from previous lecture, we have SAD divided by FU modification. And compare these two, the ratio, the modification of the ratio for small to moderate earthquake is less than the modification of the ratio for design basis earthquake in this case, in this particular case. And my question is that, is it always true? Does the equality valid for all the cases, or is case by case? That's my question for all of you. So far we have FUD star equal to 2.463, and the modification of the ratio equal to 0.3129. And then according to the equation 2-16a of the seismic design code, then we can compute the small to moderate seismic force V star equal to I, from previous lecture, I equal to 1.0, FUD stars from previous slides, FUD star equal to 2.463 divided by 4.2. Alpha y from previous lecture, we already have alpha y equal to 1.0, and then multiplied by SAD star divided by FUD star modification. And from previous slides, we already had the modification of the ratio equal to 0.3129, and then times W. And after the computation, then we have V star equal to 0.1835W. And then from previous lecture, we already had W equal to 146.05 ton force. And after substitution of W into this equation, then we have V star equal to 26.8 ton force. And then compare with the design basis seismic force from previous lecture. V equal to 0.274 W equal to 40.0 ton force. And then we have V star less than V. Therefore, the small to moderate seismic force is less than the design basis seismic force in this case. And my question is that, is the equality valid for all the cases? Is it always true, or is it case by case? And here's the reference for this course, for this lecture, Seismic Design Codes of Buildings, published in 2011 by the Ministry of Interior. And you can download the Seismic Design Code from this website. And here's the video for Lecture 1 in both English and Chinese. Lecture 2, Lecture 3, Lecture 4, Lecture 5, Lecture 6, Lecture 7, Lecture 8, Lecture 9, Lecture 10, Lecture 11, Lecture 12, and Lecture 13. And this is the current one, under construction. And this one will be the next one. And in this lecture, we concentrate on small to moderate seismic force. Small to moderate seismic force corresponding to small to moderate earthquake, and is an earthquake not induced by near-fault earthquake. It's not induced by the rupture of nearby active faults. Therefore, near-fault effect has not to be considered. It's not necessary to be considered. And under small to moderate earthquake, the structure remains elastic so that no ductility can be developed. Therefore, under this earthquake, the structure is elastic and no damage will occur. And then from previous lecture, we have considered design basis seismic force. Is the seismic force corresponding to design basis earthquake. And then under design basis earthquake, allowable ductilities can be developed so that the structure may be moderately or severely damaged. We have also talked about maximum considered seismic force, and is the seismic force corresponding to maximum considered earthquake. And then under maximum considered earthquake, the ductility capacity can be fully developed. Therefore, the structure will be severely damaged but not collapse under maximum considered earthquake. And here are two questions for you. One is V always larger than V star? Is the design basis seismic force always larger than the small to moderate seismic force? Another question for you is Vm always larger than V? Is maximum considered seismic force always larger than the design basis seismic force? That are the two questions. And here are three formulas for the calculation of small to moderate seismic force, design basic seismic force, maximum considered seismic force. That's all for this lecture. Thank you. See you next time. Bye bye.